Okay, so so welcome to the afternoon session of the first day of the Symposium on Combinatorics and Probability. So our first speaker of the session is Professor Antar Bandopadhyay from ISI Delhi, and he will talk about polynomials with non-negative coefficients, but with only real zeros and limits of combinatorial sequences. Okay, over to you, Antar.
Thank you, Apurva. It's a pleasure to be able to give this talk. Initially, when this was planned and Apurva requested me, I was very happy, but then I couldn't say yes because I just didn't have any time on the schedule which was earlier, but later it got changed, so it's good. And I'm very happy that such a workshop has been organized by Apurva and the students in ISI Kolkata. So the talk that I'm going to give today, I think it's with the spirit of this workshop is it's really an expository talk which can be accessed at a level of an MStat student, and we can see that the kind of results that we teach in our BStat and MStat program can give really non-trivial conclusions. And I'll try to draw with some modern techniques which has been developed based on quite classical statistics and probability. So it's about combinatorial sequences and it's about polynomials, but really at the end of the day, we'll see the fantastic theorem of statistics and probability, so-called the Central Limit Theorem, appears naturally. So throughout the talk, if you have any question, feel free to ask me. I don't mind if you interact. All right. So let me start the real part of the talk. So this is the schematics. We have our long introduction, and we're really going to concentrate on one particular method. So in the introduction, I'm going to discuss about 3 combinatorial sequences and related concept of generating polynomials. We'll observe that how generating polynomials and their zeros creates a strong link with those combinatorial sequences. And then we'll move to a method which is now known as Harper method, now about more than 70 years old, almost has become classical, I would say, and how it relates to more classical objects like Central Limit Theorem. And just for sake of some good calculation, at the end, I'll show you that how detailed calculation can be done using this kind of techniques. All right, so let us start with our real friend, the so-called the binomial coefficients. I think in anybody doing combinatorics, the first non-trivial thing they come across is the binomial coefficients. So what are they? I'll denote them as beta and k. They're written as n choose k in that notation. It really means that we have to select k distinct objects from a set of n distinct objects. And you all know that from our high school. So just for sake of notation in this talk, I shall denote by box n the set 1 to up to n. And we all know these numbers also appears in various different presentation of them, and one is the Pascal's triangle. We'll see that in a minute, and is the kth entry on the nth row of the Pascal's triangle. It satisfies the easy recursion that n choose k is n minus 1 choose k minus 1 plus n minus 1 choose k. In this entire talk, this recursion should play a lot of significant role. Now let us quickly see that why this recursion is true. This we know from our high school, of course. So what are we doing? We are selecting k distinct objects from n distinct objects. All right, so it can be done in 2 ways. So if we think that the objects are labeled by 1 up to n, one possibility is that all the k distinct objects were labeled from 1 to up to n minus 1. In that case, those selections are n minus 1 choose k. That's the second term. The other possibility is that no, we needed the last one. And from then the first n minus 1, we can only select k minus 1. And that's the first term. And there is no other way. These are all the possible ways k objects can be selected from labeled end objects. And we also know that this is the coefficient of x to the power k in the binomial expansion of 1 plus x raised to the n. That's the famous binomial theorem of Sir Isaac Newton, I believe. And that also we'll see later that plays a very important role. Now here is how the numbers look, and that's by the Pascal triangle, which I guess everybody here knows, that you start with 1 and you then write 1s in all the sides constantly, and then each entry is the sum total of the 2 entries which appears on before on the level before. So this is n equals to 2, n equals to continue like that and down up to 6. And of course, the numbers becomes largest at the middle and it tampers off on the either side. Now, my next number is somewhat already non-trivial. I don't know how many, there may be some of you who may not know this name at least, called the Stirling's number of first kind. So what are they? They are in general denoted by little s nk, that's the standard notation in combinatorics. So these are the number of permutations of 1 to up to n with exactly k cycles. So of course, as we know that every permutation is nothing but product of cycles. How many cycles are there is the question which is being counted here. That how many permutations are there with exactly k cycles. Okay. So that is S and K. And there is no easy formula like the binomial coefficient. Here, I think we should pause a moment and actually question this, that is the binomial coefficient n choose k, which we know there is an easy formula apparently, is n factorial by k factorial times n minus k factorial, that's in the denominator, is an easy formula? Well, it's a formula, but whether it is easy, we don't know. We will question that in a minute, but we should think about it whenever we write formula, that whether it's a formula or whether it's easy, none of those things are really so easy to say. We often say such things. But however, for the Stirling's number of the first kind, there is no such formula which one can write. However, a recursion can be written very simple argument. And the argument is exactly the same way like the way did for the recursion with the binomial coefficient. So our Stirling's number of first kind, S and K, is n minus 1 times S n minus 1 K plus S of n minus 1 K minus 1. Now the second term is very easy to understand. That counts the number of cycles, total number of permutations of where the number of cycles is k minus 1. Well, you take such a permutation of 1 up to n minus 1 and consider n as a fixed part of a permutation of 1 to up to n. That becomes a permutation of 1 up to n and has cycles exactly k. So that is one part. Now the other part is then n cannot be a fixed by the permutation. And then what can be done? Well, in that case, when you have total of k cycles you find from n minus 1 thing, how many positions do you have where n can be placed? Well, there are n minus 1 things. So you have n minus 1 position.
Sorry, question on to that. Sorry, when you said there are exactly k cycles, do you mean there are exactly k many cycles in the cycle?
No. Exactly k many cycles, correct.
So your hyphen is a typo then in the first line, because I thought it meant exactly something with k cycles. K cycle is a cycle with k components.
No, correct. Okay, fine. That's the type, I agree. So exactly k many cycles.
Okay,
so I'm counting the number of permutations with exactly k many cycles.
Right. Now the recursion.
Right.
Thanks.
Yeah. Right. Okay. All right. So thanks for that. So right, and then that's the simple argument of that recursion. Now with that recursion, if we multiply x to the power k and sum it up, Well, there is some initialization. Okay, for k equals to 0, you take it as 1, I believe. So I think I'll leave that as an exercise for the students who are present, that with that recursion written on the previous displayed equation, the polynomial is this polynomial, x times x plus 1, x plus 2, dot, 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 x plus n minus 1. It's called the increasing factorial. Right? It increases from x. So one thing I would like to note that if we go to the previous slide, sorry, not this one, to the binomial coefficient. The polynomial was 1 plus x to the power n. What are the zeros of this polynomial? All of them are real. It's multiple root of -1 n times. And this one also, they're all distinct roots, but they're all real roots. And they all have roots negative or 0. It's 0, -1, -2, all the way up to -n minus 1. Okay. Now, here is the table. These are taken from internet, because these are not so easy to calculate. Okay, but you can always do the recursion and write an R program perhaps. They grow very rapidly. So what are these rows and the columns? So the rows are n and the columns are counting for k 1, 2, etc. And there are some initialization of you consider sk, when k is 0, it is always 1. And when k is 1, it should be always the, so there is only one cycle. How many permutations are there with exactly one cycle? Does anyone have an answer to that?
Only one.
Right. Correct. So that's the number 1 which we are seeing up there. All right. Now you see these numbers grow much faster than the number of subsets of size k. Now please note, let me go back to the previous slide where we number of permutations of 1 up to n with exactly k many cycles. Now think about it. The previous one we counted what? The number of subsets of size k. There is some kind of combinatorial connection one can think about them. A and B, both of them have some kind of relation as a randomness in it. So let's think about the randomness now. That suppose I select a subset uniformly at random from n objects. That will have some size. Okay. Now, how many size k is there would tell us the probability distribution of the probability mass function, more precisely, of that random subset has size. Right? It's proportional to that. Same here, that if you take a permutation uniformly at random and count that how many cycles does it have, the probability of that number is k, is snk by total of snk. Now, what is total of snk? That's n factorial, right? The total number of permutations. And for the binomial coefficient, the total is 2 to the power n. The total can be obtained by putting, I believe, x equals to 1 in the polynomial. That's also kind of obvious. Right? All right. Now, that's the Stirling number of the second kind, and this is fairly non-trivial. So that's in general written as capital S and K. That's the number of partitions of distinct objects. Let us label them by 1 to up to n, with exactly k parts. And again, there is no easy formula. And here is the recursion, which is not so difficult to understand. So So I want to partition the set 1 up to n in exactly k parts. So one thing could be done is that from 1 up to n minus 1, I find a partition with exactly k minus 1 parts. Those are capital S n minus 1 k minus 1 many ways. And the last part would be the last object, the ns object, forms a singleton part. So that's the second term. And the first term, this is a typo by the way, it should be capital S and not little s in the first term. Okay. So, so what you do, you look at the first n minus 1 object, partition it in k parts. And capital S, it should be capital S once again. N minus 1k are the number of ways that can be done. Once you have done that, the nth object, you put it in any of the parts. That can be done in k ways. And please note that these are set partitions. And the set doesn't want to have any position for them to be put, unlike in the permutation. So that multiple is k. So the only difference with the Stirling number of the second kind from the first kind in that multiple is k. Now, when you look at the corresponding generating polynomial, unlike in the previous cases, you don't get an immediate solution, but easy to see that you get a first order differential equation as a recursion, okay, as a system of differential equations. So Hn x, if it is the generating polynomial, is x times Hn minus 1x and then ddx of Hn minus 1x. Now note that ddx is coming purely because of that factor k, because you note that even formally, you don't need to know any calculus. Formally, ddx of x to the power k, if you define it to be k times x to the power k minus 1, this polynomial differentiation will go through and will give us this particular equation. Now, what are these zeros? Could be a interesting exercise to try, but we come back to it later. Now, here is the table. These numbers grow much less fast in some sense. They are much smaller. So there are a number of partitions in k parts. So this is a picture of Sir James Stirling. And so he is of 1692 to 1770, has many contributions which you know from, even if you don't know about the Stirling's numbers, you know the Stirling's famous formula for n factorial as the same person, and many other contributions. We are just Scottish mathematician, by the way.
Sorry, by the way, does that h function hn have a, I mean, can from that equation, system of equations, one can derive something for hn, a closed form expression?
Explicitly, no, I actually probably not. No.
Okay.
But one knows a lot about it. Okay, so by the way, these polynomials are called Harper's polynomials, and we'll come back to Harper's method later.
Okay, so
I don't know why they are called Harper's polynomials. They should be called Stirling's polynomials, but they are called Harper's polynomials.
But so in particular, they will also have real roots in particular. You're going to say that? Or?
Yes, indeed. Real and negative roots.
And negative. Okay.
They have to be negative because they are generating function, right? Because their coefficients are all non-negative things. So of course, 0 is a root.
0 and negative, exactly, non-positive.
0 and negative, yeah, non-positive.
That is by somebody who is even older than your Stirling's picture, Descartes.
Right.
Descartes' rule of sign is that there are 0 sign changes, so there are 0 positive roots. So it has to be negative.
Yeah.
Assuming it is real rooted, of course.
Yeah.
Right.
All right. So now I ask this question about easy formula. 10,000 choose 5,000. Is this a large number or a small number or a moderate number? So that means you are choosing 5,000 objects from 10,000 objects. They're all distinct. How many ways it can be done? Answer is, of course, this formula apparently, 10,000 factorial divided by 5,000 factorial square. Is this large, small, or moderate? Of course, people who are attending this workshop, to you, this is not a very interesting question because you will say that, well, I will apply the Stirling formula and I'm sure I'll get an answer about it. which is indeed the case. But if you just look at it as a combinatorial object, do you get any feeling by looking at that formula, that whether it is large, small, or moderate? We'll try to calculate this later, and we'll come back to this question and settle it for ourselves, that whether it's large, small, or moderate, when we'll have a better idea about it. Similar questions can be asked. I'm just taking some random numbers in some sense, not to be understood in technical terms as random numbers, that how many permutations are there of 10,000 objects with exactly 9 cycles? Is it large, small? Or how many partitions are possible of set of size 10,000 with exactly 100 parts? Is it large, small? You immediately, of course, don't get any feeling for this question. All right. So now let's do a little bit of systematic study. So we will say any sequence, say A0, A1, A2, all the way up to AN of non-negative integers are combinatorial sequence. For example, binomial sequence, what we discussed, or Stirling numbers of first and second kind, they're all combinatorial sequences. And the generating polynomial is what we were discussing for those examples, is this guy, which we write as AX, as A0 plus A1x plus A2x squared, etc., all the way up to ANX to the power n. So that you take the kth general term, AK, multiply it with x to the power k and add it up. Then you call it a generating polynomial. The reason it's called generating, because you can determine all the coefficients from this polynomial by various ways. Of course, we have observed that in our first example, the generating polynomial is 1 plus x to the power n. And we have observed that the Stirling number of first kind, we didn't write a proof. This I leave for an homework exercise for this evening, perhaps, that from the recursion, it's very simple to prove that the generating polynomial is this product. Form is x plus 1, x plus 2, all the way up to x plus n minus 1. And the generating polynomial of the Stirling number of the second kind satisfies this equation. There is no closed form, as we discussed. Now, from a generating polynomial of a combinatorial sequence, we can always find a probability generating function by dividing by the total number. Okay. So A1, of course, is the total. So if I divide by that, and let us assume that we are not in a trivial situation where all of them are 0, because then there is nothing to study for them. So forget about such trivial scenario. So A1 is a strictly positive integer, and then we look at AX by A1, then its coefficient will be non-negative numbers between 0 and 1, and it will add up to 1. So it is a probability mass function. So this is called a probability generating function. Now, I have this statement here then, that suppose K is the random combinatorial object. What that is can lead us to much more digression. We shall not do it, but in the examples we discussed that what are the combinatorial objects which are associated, the random combinatorial objects which are associated with those combinatorial sequences. And the probability mass function for them were the coefficients of this probability generating function. In fact, they are more or less synonymous in some sense, that these probabilities results to some distribution, and whatever random variable which has that distribution would be called a random combinatorial object. Now, this description is abstract and perhaps not so desirable, because sometimes there could be a combinatorial sequence which may lead to a combinatorial object, random combinatorial object, which may or may not exist. So such detailed questions are also get asked, and we are not going to focus on that part of this theory.
But you have an
However,
example, is there a quick to understand example? I mean, or something like that that may or may not exist?
No, there are examples, but they are not so easy to understand, because it becomes very difficult to get a counter example. Whatever you will in general think, you will be able to perhaps construct one. Now, of course, abstractly there is a construction. Okay, so when I say something which is not there, it means in a canonical way. Now that's where the problem becomes, that what is canonical and what is not canonical.
Right.
So let us not digress there.
Okay.
So for the three examples, they are very concrete objects. For the binomial coefficient, the object is the randomly selected subset. For the Stirling number of the first kind, it is a random permutation, and you get to count the number of cycles. And for the Stirling number of the second kind, it is a random partition, and you get to count the number of parts of the partition.
So really there are two components to your random combinatorial object, right? One is the thing that you select and one is the value you assign, like a random variable.
Correct. Absolutely.
Okay.
Absolutely. And I'm going to really deal with both,
Right.
and see how properties of one can result to some properties of the other and vice versa. Naturally, as we call in our classes, that this P is a probability generating function. And these are just the what I said about the random objects, which we have already discussed. So let me move on to the next slide. So now you see, for finite n and some fixed k, we can try to calculate this. Sometimes achievable and sometimes are not. But when n becomes large, what are these objects look like? What are these numbers, the counts look like? How much they are? That is the question which we would be interested to answer in this talk. So essentially, technically, what happens if n tends to infinity? And how does the objects behave? Now, here, this random object itself is also of interest sometimes, that for sufficiently large n, what are the random properties of those of randomly selected combinatorial objects? Can be also of interest. Now, I'm being vague here. We definitely need a more precise statement. That's what it really means. We'll see what are the specific examples where we can write specific precise statements. Sometimes we can. But intuitively, it is important to understand them. We can think of answering them in the following way, that for large n, at what value the random object will concentrate, which means that, well, is it the case that when n becomes larger and larger, there are few values which are more likely to happen and rest are not so likely to happen? That would be the kind of the way we will try to understand it. And if it really concentrates, then, well, it concentrates, that doesn't mean it becomes one, perhaps. Then there would be deviations, and how much are the deviations, if at all there is a concentration? So these are the intuitive feelings around them. To be more precise, one should ask the question that how the random object is distributed. And that, of course, to our students who are attending, makes much more sense than the intuitive feeling. But the intuitive feelings are also very, very important, because if you don't have a feeling, it sometimes becomes very difficult to really even understand or to interpret it. All right, now let us go back to the example, and I'm perhaps going to show you these things all you know, that binomial coefficients would result to the so-called famous binomial distribution of a pair coin toss distribution. How do you select the random object then? That you toss n coins independently, unbiased, and look at wherever the heads that appear, and those are the places where you take. So what is the distribution of Kn? Namely, the size of the random object, which we just now discussed, is the binomial distribution. So you write it in this way. A least, as what was taught to me by my teacher, from whom I learned a lot of probability, Professor B.V. Rao, that a distribution for such cases is a least, the table, they got the values and the probability. It's easier to said than done. And in general, a picture speaks a lot more. than anything else. So here is a schematic of a binomial distribution with n10, so 10 trials and unbiased, with probability half. So whatever I have drawn are the frequencies, the probabilities. They're not just the frequencies, but the probabilities. So they're proportions, which is nice and symmetric, as we know. All I'm going to do in this little movie that I'm going to increase the number of trials. So by the way, the scale is being changed. Okay, so this is something I'm deliberately doing. So here you see the scale is, of course, to begin with it was 10, now it is 20. It's being put into the same little box. So they are getting squeezed, and they are more getting squeezed as the number of trials increases, and they now look like a curve, no more line standing. And the reason they look like a filled in, because all those lines are anywhere there, down up to 10,000. When you do it up to 10,000 in that box, it really looks like a filled in space. Now, how exactly the curve looks like? That looks like a bell-shaped curve, like a bell, what you find in a temple or in a church. But it really looks like that. We'll come back to it again. I don't know, I'm sure the students must have seen these many times, but this little movie is quite interesting to students who probably are not necessarily so familiar with probability, but say much familiar with combinatorics. Now here is a definition, I'll say. Now please note that is a definition, it's not a theorem, okay? And I call the definition Central Limit Theorem for combinatorial sequences. And it's not a theorem, it's a definition. That suppose I have a combinatorial sequence A0, A1, AN. Each combinatorial sequence may depend on N, just like the binomial, for example, it depends on K and depends on N, N choose K, or Stirling's number of first or second kind, etc. The combinatorial sequence with generating polynomials P and K are the generating polynomial A, and P and Ks are my proportions, or the probabilities from this.
Formally, should that capital A be capital A?
We'll say that a central limit theorem holds for this sequence if there exists two constants which may depend on n, mu n and sigma n, positive, such that if we look at this type of a sum of those probabilities, that I'm summing all those P and Ks such that K is less or equals to mu n plus x sigma n minus integral of minus infinity to x e to the power minus t square by 2. I'm missing 1 over square root of 2 pi. That's sacrilegious. So please consider that is there, that 1 over square root of 2 pi dt. And a supremum of the absolute difference, and as limit n tends to infinity, gets 0. Then we say that such a combinatorial sequence admits a central limit theorem. Or a central limit theorem holds for such sequence.
So can you hear me, Antar?
Now, here is Harper's theorem. Okay, that's a beautiful theorem.
Just
you
one
first see it, then you will feel really find it.
Maybe his speaker is.
I'll unravel it. Now, what is it? You have a combinatorial sequence, and you have the generating polynomial A. And suppose A has all real zeros, say alpha 1, alpha 2, all the way up to alpha n. Okay. So you can always write that as theta I, say I write 1 over 1 minus alpha I. That makes sense, right? Because these alphas are all real zeros, which we are going to take to be negative. Didn't I mention that? Probably I didn't mention that. There are only real zeros, say alpha 1 to alpha n, which are all negative. Okay. And you look at theta I, which is 1 by 1 minus alpha I, that should have been mentioned, that it's all negative. Mu n is the sum of theta I, and sigma n square is sum of hello. Oh, no. Okay, hold on. Let me. One.
Can you hear me now, Antar? Can you hear me?
Can you hear?
I can hear you, yes. You can't hear us, is it?
Now even we can't hear Antar.
Yeah. No, both are gone.
Again phone করতে হবে.
Maybe I'll call you. No, I think you just said something. No.
Yeah, I can hear you now.
Oh, you can hear me. Okay, very good. Very good. Sorry, if you can go back a couple of slides.
Now, hold on. Let me first make it full screen.
Thank you. Sorry, in the CLT definition for combinatorial sequences.
Yeah.
I don't know what.
That should be 1 over square root of 2 pi.
Of course. So first of all, the capital A should be capital A subscript n, right? Because you're defining it row by row.
Absolutely. Absolutely.
Right. And then the second is, sorry, this is convergence by law. I forget now. I'm forgetting all my probability.
Whatever I have written here
Yes.
is actually result to convergence by law, but it is little bit more than that.
Actually, because the
This
mu and
is
sigma
in a very technical term. What I'm asking is the convergence in Kolmogorov distance.
Okay, Kolmogorov distance.
Yeah.
That is, as far as I know, the law is not metrized by Kolmogorov, right? It's a Prokhorov or something.
Now, the thing is that in this particular context, they happen to be equivalent.
Yeah.
Okay.
So, but that need not be true in general, but in this context, they will be equivalent because my limiting distribution, as we all know, is the Gaussian, which is continuous, and hence everything would be very nice and smooth. These are very technical things we are saying. I'm not going to keep the talk at that technical level.
Okay, thanks.
Any other question was there which I couldn't hear?
That was the only one, sorry.
Oh, all right. Okay. So then to Harper's theorem, here also there is a typo once again, that A has only real zeros indeed, and my zeros are alpha and alpha to alpha n. And well, I now see why I didn't mention that. Because you see, as I discussed, that it's a combinatorial sequence, right? If it has real zeros, the zeros cannot be a positive number.
Right.
Right. So that's why they have to be negative. So that the assumption doesn't need to be made. So now I have my theta is that 1 over 1 minus alpha I, and my mu n is sum of theta i's, and sigma n square is theta I times 1 minus theta I. These all looks very familiar, yet very interesting. And then the theorem says, Harper's theorem, that the central limit theorem holds with mu n and sigma n, provided of course sigma n goes to infinity as n tends to infinity. So that's Harper's theorem. Now the remark I have is that the above statement is often abbreviated in terms of the associated random combinatorial object, which if we denote it by Kn, that Kn minus mu n by sigma n converges in distribution to normal zero. Now that was the technical discussion which we had, that this is like weak limit, a little bit more than that, but for these combinatorial sequences and the fact that we have a normal distribution, these are equivalent. All right.
Actually, maybe I don't know if I should ask here or not. Okay. Yeah. This is very exact. This is very universal. Is there a similar analogous result for convergence in distribution to the exponential variable, standard exponential?
When we will see the reason for it, we will also see that such a thing for combinatorial sequences is not quite possible.
For exponential variables, it's not quite possible, right?
Not quite possible. You have to be within normal and nothing else.
Right. Yeah, maybe not combinatorial sequences, but other things.
Others may. Of course, others may. Now, one another thing I'd like to point out here, I don't know whether my cursor can be visible. So this fact that sigma n goes to infinity is a very important assumption. Now, if that doesn't happen, then many other limits can be obtained. But whether they can be computed can become a very difficult.
So I'll tell you the reason why I'm asking. It's because of something in analysis, which was studied by Laguerre and Collier again at the turn of the 20th century,
Right.
19th century, which is that if you look at polynomials with real zeros, and you look at sort of limits of such polynomials on which converge uniformly on compact sets. So these are all defined by polynomials. So they converge on the real line, but locally uniformly on compact sets.
Right.
Then the limit is the limiting functions are very, very specific, and they're functions called the Laguerre-Collier class. And they come up exactly, they're basically products of exponentials and linear factors and a Gaussians. So basically, that was what I was sort of wondering if here, of course, your coefficients are integers or rationals, if you will, in sequences and so on. That need not be the case in the more general setting.
Right, exactly.
But that's why I was asking.
And also, Apurva, the sigma n goes to infinity is very important.
That's
if
critical.
sigma n is finite, then we can have many strange distributions, but those are very, in general, you really have to construct them. They are not very, what to say, let's say quote unquote, not naturally appearing.
And they could go beyond normal and exponential, which is all that.
Yeah.
Okay, thank you.
Yeah, it's kind of a degenerative. But
right. Okay. Right.
All right. So one thing, what we were really discussing, that there is a lot of this universality of this limit. That is the only one thing, and which is there also in the part of the definition. If you think that the definition gives a specific formula for the thing which we are subtracting, that has nothing to do with a0, a1, etc. E to the power minus t square by 2 divided by square root of 2 pi being integrated. That's a very specific function. So that's where the universality lies. The limiting distribution is called a normal distribution, which looks like a bell-shaped curve, as we all know. And this is the man who discovered this theorem, L.H. Harper. Is currently professor of emeritus in the UC Riverside in USA. All right. So now for example 1, if we try to just go through Harper's method or Harper's theorem, we know that all the zeros are -1. So what are the theta's? They are half. What is then mu n is n by 2. What is sigma n is square root of n by 2. And we get our well-known central limit theorem, that Kn is the size of an uniformly selected subset of 1 to up to n. That's the binomial random variable minus its mean, n by 2, divided by its standard, results to a normal distribution. And this is the De Moivre-Laplace central limit theorem, which was discovered in 1738 by De Moivre and was later made rigorous by Laplace. De Moivre, I think, was a Danish mathematician, and Laplace, of course, was French. Here are their pictures, which I got from.
Actually, sir, De Moivre was French. I think so. He was French, and he was Huguenot, and he went to England for seeking religious refuge.
All right, possible. I thought he was a Danish mathematician. Maybe I am wrong in my history, but thanks for that. And Laplace, of course, was a French mathematician. If you see, they did not quite overlap, but definitely did not collaborate. So 1617 to 1754, and De Moivre-Laplace central limit theorem, as per record, it seems it's 1738. So that's a long way back this was discovered. And Laplace proved it using a method which is very similar to Harper's method. Now, for the Stirling's number of the first kind, as we have already observed.
Actually, this is fascinating. I just saw in Wikipedia that De Moivre, as he said, was French, moved to England, and was a friend of Newton and Stirling. So this whole thing of Stirling's numbers and the central limit theorem seems to be their friendship.
Well, they were all connected in some sense, right? Yeah, in those days. So, like in these days also, I believe. So now to the Stirling's number of the first kind. So my zeros are 0, 1, -1, -2, etc. So I can use the formula to get my theta i's to be 1 over I now, right? It is 1 by 1 minus alpha I, right? So I get 1 by I, and hence that the mu n is of the order log n. And sigma n square is also of the order log n. That's the harmonic series.
Sir, is this because that 1 by I square, this converges to pi square by 6, and the 1 by I it diverges, so that term obviously dominates over that, and so it's order of log n.
Correct, exactly. But when you say dominate, that's why that little twiggle that what we are looking at is asymptotic.
Yes,
so
so then that pi square by 6, that's a finite. That will be that part will be going to 0, and that will be close to 1.
Correct, absolutely right. That is absolutely the right thing. That's the reason why the mu n and sigma n have the same asymptotic order, is what they say. And hence that the random object, which is the number of cycles of a uniformly selected permutation, has the following type of results in the combinatorial sequence having a CLT is kn minus log n by square root of log n converges to the Gaussian or the normal distribution. Okay. Now for the Stirling number of the second kind. Now here is this bullet point, which I feel that I'm not sure that whether Apurva will agree with me that the students can be asked to do this. It's not so difficult to show that this case also the zeros of the generating polynomials are all real. Of course, 0 is a 0. Now, why should quickly that such polynomial will have all zeros real? Anyone has any quick thought? All right. So you see, if you do it by induction, very simple proof can be written. So suppose hn minus 1 has that property. Then hn would necessarily have that property because of what reason? Are the zeros of hn minus 1 and hn are same except for 0? So if alpha is a root of hn minus 1, would that be a root of hn if alpha is not 0?
You're saying again by induction using the recursion thing.
Correct. Yeah. It's recursion and induction too. See, the recursion anyway gives this differential equation. We don't need to see it as a differential equation. You can just see it as formally.
Yeah, call that hn minus. Oh. No, I don't.
Why would the term involving the derivative also be 0 at the root of hn minus 1?
Yes.
No, it won't be, right? It need not
Oh,
be.
okay.
That's what I'm saying, that if you have a 0 of hn minus 1, which is non-zero, okay? So alpha is alpha not equals to 0 and alpha is a 0 of hn minus 1, then that's not going to be a 0 for hn.
But
So
sir,
there may be repeated root, right? Means like multiplicity may be.
There can be multiplicity. There can be multiplicity.
In that case, there will be repeated a common root.
and that root will be the same as that of HNX.
Correct. If there is a multiple.
Yes. But how do we get? But how can we guarantee when that suppose this HNX has even a multiple root, or does this necessarily have some the only zeros which are distinct?
Those are all should be part of the proof. Those are all right questions which we are asking.
Right. So you're saying multiple.
Let me ask you a different question. Suppose I have a polynomial, okay, which has 2 real roots. I have a polynomial which has 2 real roots. Then is it not true that the derivative of the polynomial will have a real root?
Yes, sir. Goes through.
Yes, it is true.
Sorry?
Yes, it's true.
Yeah, somebody said Rolle's theorem. Yes.
Okay. All right. Okay, so that's the hint I will leave for you to do this, because this is a very simple,
Yes,
I think not even BSTAT level, even a high school level exercise.
if there is a root which has multiplicity 1, then at that point the derivative changes sign. So between those 2 points, between any two roots,
There are no multiple roots in this case.
yeah, if there
Recursion will not have multiple roots.
Yes, yes.
But what we need to take into account that of the sign also, because there's an x multiplied with that.
No, but please remember, that was Kostov, right?
Yes.
Right. So please remember that it's a generating polynomial of a combinatorial sequence. So it cannot have a positive root. Okay?
So it will have a negative root.
All roots are 0 or negative. 0 is a root.
Yes.
And negative numbers. Now the next statement, hold on, sorry. Next statement is actually difficult, and I really don't have time to tell you how to do this. But what one can show that mu n has the following asymptotic, that it is n over Rn and sigma n square is n over Rn square, where Rn is the unique solution of this equation. Rn times e to the power Rn is equals to n. And Apurva, I think here somewhere the kind of things which you were saying actually comes into play. The exponential function becomes very important.
Okay. Okay.
By the way, that particular equation, differential equation, one can try to solve, right? If you multiply by e to the power x on both sides, you will get something by the
Product
chain rule formula.
Yeah. Product rule. But there's also an x factor, which is interesting.
Yeah, forget about the x.
Yeah.
And
then yes, sure.
Yeah.
F plus F prime.
All right. So those are all hints towards how to solve the root problem. But the third bullet point is of course non-trivial. And I'm not going to show you a proof of that. You can look at any book on combinatorics, I believe. Now in 1920, I think, and I put a question mark because it's not absolutely clear to me that that's the right year, Levy, a very famous probabilist, now we have moved to 20th century, okay, proves the following, that suppose I have a combinatorial sequence A0 to AN with generating polynomial A and assume it has all real roots, alpha 1, alpha 2, alpha n, and let's write theta I is 1 over 1 minus alpha I, then there exists independent Bernoulli random variables xi with expected value as theta I, such that the corresponding random combinatorial object, namely Kn, has the distribution same as x1 plus x2 all the way up to xn. These xi's are independent Bernoulli triads. Now please note that theta I is of course a number between 0 and 1, because alpha i's are all negative, so 1 minus alpha I is larger than 1. Now, why is this result true? So you look at the assumption would tell us that ax by a1 is product in this form, right? Because all the roots are real, so that is x minus alpha I by 1 minus alpha I. So if we look at the probability generating function of the random object Kn, can be written as, now let's recall what is my theta I. Theta I is 1 over 1 minus alpha I. So if we look at the probability generating function, ax by a1 is this product, right? This is theta I x plus 1 minus theta I. Right? Because theta is 1 over 1 minus alpha I. So if you look at the first bullet, that gives me this formula for Px. Px is Ax by A1. And of course, theta I x plus 1 minus theta I is so-called the generating function of a Bernoulli random variable with mean theta I. So Px is product of the generating function of Bernoulli variables. So that means whatever random object Px represents would be sum, independent sum of the random objects which are Bernoulli triads of this individual linear product parts. Now I think I can tell you quickly a proof of Harper's theorem. So we have Kn is sum of x1, x2, xn. Each xi is Bernoulli theta I. The mathematical expectation is linear. So mu n is expected value of Kn. And sigma n square is variance of Kn, because that is sum of the variances, because they're independent. And that theta I times 1 minus theta I, that was the by definition in sigma n square. Finally, we need to use a more rigorous version of the famous law of error of Gauss of 1809. That's the law which I would like to state, and I don't know whether many of the students actually have ever seen, even though they know Central Limit Theorem. So the distribution of small amount of independent but identical standardized error when added a large number of times is given by a bell-shaped curve. And then Gauss gave the explicit formula for the bell-shaped curve. There are many bell-shaped curves, by the way, but this is the one which Gauss wrote, that 1 over square root of 2 pi divided by minus x squared by 2. That's 1809, by the way. Gauss did not write a proof. It took many number of years, 1920 perhaps. In fact, it's not perhaps, it is. Now, when so-called the famous IID Central Limit Theorem, which I believe everybody present here knows, of Levy and Lindbergh, was proved. And that's as follows, that if you sum up IID random variables with mean mu and variance sigma square strictly positive, then you look at such probabilities. The sum is denoted by Sn. We in general call it the random walk. So Sn minus n times mu divided by square root of n sigma. That is the scale, the standardization. Lesser equals to t, this probability will converge to the integral of the bell-shaped curve. Please see, there is the analogies that small amount of independent but identical standardized errors. Why is it small amount? Because we have standardized it. Why is it an error? It is the difference of the value of the random walk to its mean. So it's the deviation. That's what is error. They're identical. What are we summing? We are not summing Sn minus n mu. If you unravel it, what we are summing is y1 minus mu by square root of n sigma plus y2 minus mu by square root of n sigma plus y3 minus mu by square root of n sigma, etc.
Sir, that should be x between minus infinity to infinity or t between minus infinity to infinity.
Say it again. T between minus infinity. Thanks for that. That's also a typo. There should be t between minus infinity. X is also between minus infinity and infinity, but what is important here is t. Now, those little values, yi minus mu by sigma, are the standardized errors. Mu is the mean, y is the random value, its difference by sigma is the standardized one. And why is it small? Because we are dividing by the scale square root of n. So we are putting into, or in Galton's word, we have marshaled them into a standardized scale that will give us the bell-shaped curve. So this result, I think many of you know a proof, and my students who are present would see a proof in about 2 weeks' time. This is Frederick Gauss, 1717 to 1777 to 1855. The normal distribution, which we know in statistics, is most often known as Gaussian distribution in various parts of mathematics. Name of Gauss, I believe. And this is Paul Levy. Now, he is almost of our time, not of very old, right? 1886 to 1971, a French probabilist. So now, so this is, of course, a very powerful result in probability theory and statistics. I think you have used many number of times, even if you haven't seen the proof. In a very recent days, Terence Tao has termed it as one of the most important results in mathematics. Some of the reasons are because it really gives us control on various asymptotics. So the IID CLT is a modern version of the Gauss's law of error due to Lindbergh and Levy, which we already discussed. But unfortunately, it is not enough to prove the Harper's method. We need a little bit more, and this is something what in general is students of MSTAT would perhaps know, but not otherwise, that if we have independent Bernoulli trials, then you subtract the mean. So you look at the sum of independent Bernoulli trials. They need not be identical, by the way. You subtract the mean, you divide by the standard error. Even then, the Gauss's law of error holds. Once again, that typo x should be t, provided variance goes to infinity. And this is Lindbergh's theorem. And this more general result can be proved. And in general, I think people learn this in the master level. Of course, expectation of Sn in our case is sum of the thetas, and the variance of Sn is sum of theta times 1 minus theta. And of course, then the standard error is square root of that. And that is my mu n and sigma. So this will complete the Harper's method.
Hello, sir.
Yes.
So where the xi's were independent?
My yi's are xi's are independent, yes, Chandramouli, because you see, those are generating function is product of generating function, right? If you have independent random variable and you add them, then you get product of the generating function, and vice versa. Vice versa is a theorem which is a little more difficult. But if you have product of two generating function, that's a generating function of the sum of two independent random variables, having each of the generating functions. Right.
Okay, thank you, sir.
Sir, we need this version because in the Harper's proving Harper's method, we don't know, we need not assume the independence, because for the random combinatorial object what you are mentioning, that AIs might be somewhat related, or is this something?
No, they are independent, but they are not identically distributed. Let me go back right here. That if you look at this, the probability generating function is product of generating functions of various Bernoulli random variables.
Yes, that means that they must be independent.
Independent, but not identically distributed. They will be identically distributed if all the roots are same. That is the case in the binomial case.
Yes.
Okay, and that leads to the de Moivre-Laplace central limit theorem.
And for the cases we are getting the rather weird versions of not exactly de Moivre, but using that idea we got different kinds of central limit theorem looking rather weird.
Not weird, but it's still universal, right? The final limiting code did not change.
But they look a little weird to me.
All right. Okay, but the limit is same. It's Gaussian. Right. Okay, so this is Lindbergh. Lindbergh and Levy, again, I don't think they overlapped. I think Lindbergh was a Norwegian or Swedish mathematician, Levy, French mathematician. They probably worked independently. Now we need more precise result to prove thing which we are interested. For example, 10,000 choose 5,000. So more precise result can also be derived, that exact probability mass function approximation can be done using the same technique of Harper's method, but one need again going back to help of Laplace. So there is a fantastic analytic technique which I think Apurva also mentioned, the Laplace's method, that needs a lot of analysis need to be done, and using
the
that,
the Laplace transform is this magical thing, right? That turns
Right.
convolution to products.
Yeah.
Basically.
Yeah.
Exactly.
And then you integrate around line or a contour again around it. So that's a fantastic method, and probably the only real method in analysis which helps us to do lots of asymptotic. And with that, one can do such precise formula, and those for this particular context were done by two famous probabilists, Nedengo and Kolmogorov, and later on that's called the Nedengo-Kolmogorov local limit theorem. These are not results which we in general cover in MSTAT event. Nedengo was a student of Kolmogorov, and this is Professor Nedengo, 1912 to 1995. So we are almost reaching to our time. And this is Professor Kolmogorov. Now, who is Professor Kolmogorov here? Can anyone identify? There are a lot of people here.
Just behind that table, just sitting there at the table. That means at the back side, as far as I can see.
Right, Gustav, you are absolutely right. The person who is wearing the fully Bengali dress is Professor Kolmogorov. This is taken in Amropali. This is a picture from ISI archive. So this is in 1962 in Amropali. That's the residence of Professor Mahalanobis. We still have that building, but now it is not accessible anymore, unfortunately. And he's surrounded by his students and famous stars of statistics and probability from this country. So from left is Professor K.R. Parthasarathi, who is a faculty in ISI Delhi, emeritus now, has worked with Professor Kolmogorov almost like a student. The PhD is not with Professor Kolmogorov, but he worked extensively with him. Then Professor B.P. Odhikari, who was our second director of the institute. Then Professor S.R.S. Baradan, a Nobel Prize winner, and also a fantastic mathematician and probabilist. Then Professor J. Sethuraman is a very famous statistician, now retired. And then Professor C.R. Rao, all of them earlier whose name appeared, except for Kolmogorov, students of Professor C.R. Rao. And then P.K. Pathak. Now, of P.K. Pathak, I don't know much, but since Rajiv Da is present in the audience, he can perhaps tell us that what happened to P.K. Pathak. Maybe later.
Well, P.K. Pathak is a statistician.
Professor Rao, yeah, please.
Yeah, he is a statistician. He is right now at East Lansing, Michigan State University.
I see.
Yeah.
So of the contemporary of Sethuraman.
Right, yeah.
Right. All right. So I think that is more or less my talk. And I'm glad to notice that Professor Rao was present in the talk, and I didn't notice it before, because then I would have been far more, I don't know, nervous perhaps, because it is not any time easy to give a talk to your teacher who has really taught you all the probability. But thank you for being present in the talk. So some numerical answers which we can derive from Nedengo-Kolmogorov theory or all the Harper's method which we discussed. So let's see, 10,000 choose 5,000. If I divide it by 2 to the power 10,000, then this is approximately 1 over square root of 5,000 pi is what Harper's method takes us. And that is approximately 0.008 or 0.8%. So proportion of subsets of size 5,000 from 10,000 objects, proportion, okay, is about 0.8%. Of course, the total number of subsets is really large, but the proportion of those which are exactly 5,000 is 0.8%. Now, each one of you decide that whether the number 10,000 to 5,000 is large, moderate, or small for you to think. Please note that that number would be approximately 0.008 times 2 to the power 10,000. Now, 2 to the power 10,000 is a very large number. The proportion of permutations with exactly n cycles of 10,000 objects. If we do that calculation with the Harper's method, we need to have the log and the pi or square root of 2 pi because of the normal distribution. Comes out to be 13.12%. Of course, the total exact number need to be multiplied with 10,000 factorial, which is a very large number. I would call the first one is really small, and this one is somewhat moderate. But that's me. You can decide whatever. Now, if you go to the Stirling's number, the question what I had was the 10,000 size set with 100 parts. The number is almost 0% when you do that. They don't grow that fast. I think I'll stop here. I think I'm a little over time already. So thank you.
Okay, so thank you very much for a wonderful talk, Antar. And are there more questions? Given we asked enough during, but are there any other further questions before I stop recording?
Any reference of Harper method?
Reference of Harper method. Right. You see, Harper's paper is there from 1952, I think. But a better reference is to look at the soft load lecture notes by G. Pittman when he talked about a combinatorial, random combinatorial objects. So that I think from 2002 or 2001, I don't remember exactly. So that's a fantastic lecture notes which one can see. And there are many more things there. Many other random combinatorial objects, and he also connects it to much non-trivial things which called Bessel processes. So Harper's method has much bearing on modern probability theory. So soft load lecture notes of Jim Pittman.
Do some random graphs also fall in this setup or no?
Well, means as such the random graphs which we think in general when one see here at the word random graph, they won't. But you see, various combinatorial objects do fall. For example, suppose you think about so you take an n-gon and you create a random graph by drawing random diagonals. So they will fall in this type of domain. So you have to have some kind of combinatorics playing in the behind. But Professor, as such, there is nothing wrong in considering these generating functions as an abstract object. And then many things will fall in it. But whether the zeros would be all real can become an issue.
No, I am basically thinking of graphs on n vertices with k edges.
You
That
mean the classical Erdős-Rényi? Classical Erdős-Rényi, you will not, strictly speaking, will not fall in this. But
No, I'm not thinking of Erdős-Rényi. For example, A and K is the number of graphs on n vertices with exactly k edges. Okay.
That would fall in this. That is also classical Erdős-Rényi. They are called binomial random graphs. And their asymptotics. Well, you see, now it depends on what statistics you are looking at. Okay. So the graph is it's not really a number, right? So it depends on what statistics you are looking at. Some statistics would fall in this one.
Okay.
Quickly, one thing is very simple, that if you take the binomial random graph and you count the number of edges, that's binomial. And hence it falls in this domain. So it depends on which statistics you are looking at.
I see. Yeah.
More questions? Okay, if not, then let's. Sorry, go ahead. Yes.
For proving Levy's theorem, we need a showing existence of random variables. And
Very good question. No. To prove Levy's theorem, whether you need to. So which Levy's theorem you want to prove? This one, or you want to prove the previous one?
yes, the previous one.
So this guarantees the random object. This guarantees a random object, but this is by an abstract way, okay? So the problem is to relate it to your combinatorial object.
Yes, that.
So it may or may not be possible. Not always. Sometimes it can be done. The 3 examples which I've given are of that type. They are called canonical examples.
But yes, but is it always constructible? Question.
No, not on the same probability space. You may have to expand the probability space.
Okay.
So in Pittman's lecture note, there is an example, but the example is fairly non-trivial.
So can you please share with us the link, because it is quite unavailable in Professor Pittman's website.
Maybe I'll share the link with Apurva, because I don't have your, or do I have your?
No, you are more likely to have his address than me.
All right. Okay. Easier would be that you send me an email and then I'll respond with lecture note. Okay.
In what email? Your IInd email?
Yes. Right. I'll show you my email. Oh, I have it there. There is my web page, and you can find all my contacts there. Okay.
Okay. Thank you, sir.
Yeah.
More questions?
Oh, sorry. I stopped sharing.
Okay, I think now there are no more. So let's thank the speaker once again for a very nice talk.
Thank you so much.